All right, so good afternoon, everyone. So let's start today's lecture. And in the last lecture, we basically do two things, right? The first thing is that we introduce the fundamental basic laws we are going to use to study the fluid dynamics. Okay, fluid dynamics means that when fluid is in motion, okay? And those fundamental laws, including the conservation of the mass, Newton's second law, or in another word, conservation of the linear momentum, and also the principle of angular momentum with the torque, and energy conservation. Energy conservation is also called the first law of thermodynamics, right? And the last one is the second law of the thermodynamics. And this is the first thing we did in the last lecture. The second thing we did is that we give those fundamental laws, okay, what their equation will be in a system, in a closed system. And since those laws are directly applied to a mass of matter, right? So it's very easy to write those equations for a system. And we also seeing that in the fluid dynamics, okay, we are using the concept control volume more than using the closed system, because that the control volume usually can be very control volume formula, okay, which will be more easily to use in the real application. And so for that purpose, we need to derive a transfer. We need to derive some correlation, okay, so that we can convert the formula we get for those basic laws under a closed system and into a new form which is working for open control volume. All right, and to do that, we first try to derive a correlation that to relate it, that if we want to calculate a derivative of quantity, right, in a closed system, how we can express the same derivative in a control volume. And this equation is what we this equation here is what we get at the end of the class lecture and last class. It's basically telling us that okay, the derivative of a conserved quantity, okay, inside a system will be equal to these two terms. And the first term, okay, the first term on the right hand side basically is that the change, okay, this conserved quantity, inside inside the control volume. And the second term is actually the net rate, okay, of this conservative flowing out from this control volume through the control surface. Okay, so this correlation is basically the fundamental correlation between the derivative inside the system and the derivative quantity derivative inside control volume. All right, and this n and eta, okay, can represent using the different values, okay, which is given here. If n is m, then eta will be 1, so that is for the conservation of mass. And when n equal to p, which is the linear momentum, and eta is v, so we can that the equation we derived there is will be to calculate the derivative of your linear momentum. And also h is angular momentum, and E is total energy, and S is entropy, and so on. Okay, so with these correlations we developed, so now we are going to try to go back to the fundamental laws we have and try to see that what those fundamental laws, what their mass formula will be inside the control volume system, control volume method. Okay, and let's start in the first one, and which is also a easier one to to use. Let's consider the conservation of the mass, right? In the conservation of mass, simply we make this n equal to big M, which is the mass, and make eta equal to 1. Okay, and so if we bring that, okay, this is the how we write the conservation of the mass law in a system. Simply means that because system is closed, right, and there is no change of the mass regarding to the time. So in another word, the mass inside the closed system is constant. Okay, and the mass can be calculated from the density and the volume of the system. So we can write this way. Okay, so if you do the d derivative on time on system, so is you just using replace this using m here for the n and using 1 for the eta, we immediately get this correlation here. Okay, so on the left hand side, this is the derivative of a big M on the system. On the right hand side will be the derivative, the same derivative but under the control volume. And you substitute this correlation here back into this original conservation equation. And so what we get, we will get the final form, which is the formula of the conservation, mass conservation, in a control volume. Okay, so this is the mass conservation in a closed system, and this will be the mass conservation for control volume. All right, and so now you see that this two is different. Okay, and the way we convert from this one to this one is because we're using these correlations from system derivative to the control volume formulation, or control derivative in control volume. So we're using this method here, and the way we derive this formula is through that those this is this graphical correlations we do that we do in the last class, okay, to derive that derivative correlation between the system and control volume. All right, so let's take a look at this new equation we got, okay, for the mass conservation. So we have two terms, right? And let's study the physical meaning of each term. So we can, put this term from the left hand side to the right hand side, okay? And so we can write in this way, from this equation, from the original equation, we simply put this this is surface flux term to the right hand side, so we have a minus sign there, okay? And what is two terms physical meaning of it? Like if you look at the left one, okay, the term on the left hand side, so this is density, and this is integration of the density on the volume, right? So when you get here, this integration will give you the total mass under this inside this control volume, and you have the partial t, which means that this is the rate, okay, of the change of the mass inside the control volume. Okay, so if this is larger, this value is become larger than 0, which means that your mass will be increased. Okay, if this value become negative value, this whole become negative value, that means that your mass will become inside your control volume will become decreased. And if you look at the right hand side, okay, and remember what's the meaning of this term here. And this is the flux term, okay, through the control surface, right? And basically is this term here, and we're seeing that the meaning of this one, this is this is the net rate, okay. So this is the net flux of this volume flowing out of the control volume, right? And if you add a negative sign, and if you add a negative sign of it, what does this mean? So this volume, this term itself is a net, okay, mass flux flowing out from this control volume, right? And if you add a minus sign, that simply means that this will become the net mass flux flow into this control volume, right? Because without this negative sign, it will be the flowing out, what the flux, mass flux flowing out. And after you add a negative sign, so you just reverse the direction of the flow. So this will become the net of mass flux flow into this control volume. Okay, so this will be so this will make this a very physically this make this whole equation become meaningful, right? So the increase of the mass inside of the control volume, it just will be equal to that how much of the mass will flow into this control volume, right? So this left hand side will be the rate of the increase of the control volume if this is larger than 0, okay? And the right hand side, if it is larger than 0, that means that this will be the net of influx of the mass, okay? So this will be the mass conservation equation, what's the physical meaning for this formula, okay? mass conservation formula under the control volume. And let's consider several special cases here. Okay, so from this equation here, let's first consider that a special case that if we have an incompressible fluid, and we introduce incompressible fluids at the end of the last chapter, right? So it basically means that that means the density is not changed. And in that case, you can take this rho out from this integration, okay? And also on the surface, flux, mass flux integration, you can also take this rho out, okay? And then you can divide it by, you can try to divide it by rho on the both sides, so rho will disappear. And for this one, your integration on the dV, okay? This is the volume. Your integration of the whole volume on a control volume. So the result will just give you the volume of your control volume. Okay, so this one just give you V. So the reason, so this term will become dV over dt. Okay, and the surface flux term will still be this one. All right, and usually, okay, when we define the control volume, we define it on the location, right? And also we want it, in most of the time, right? We won't let it change with the time, this location, control volume location. So which means that the size of this control volume, in most cases, it will not be changed, okay? So let's consider that this V will also, this volume V, okay, not this velocity V. This volume V is also a constant, won't change with time, this control volume. And so we can assume this V is constant, so this term will also go. And the only thing left is this surface flux term, integration term, okay? And it's basically fundamentally saying that, okay, so if you have constant density in compressible fluid, and also if you have your control volume size, volume, okay, is constant, then the integration of all your surface, mass flux around the whole, control surface will just become equal to 0. Okay, this CS is the control surface, which is the interface of your control volume, right? The boundary of your control volume you define. Okay, so this is so this will be the final equation for this special case. Okay, for the conservation of mass, it's much more simplified than this original one. Okay, and when the density is constant and when the control volume is this V is also constant. And for some special cases, okay, like we for the special cases that if we only have like flow through a pipe, okay, like through a pipe with some joint, through some with several inlet and with several outlet, and also if you assume that the velocity at the inlet and at the outlet, okay, on each individual inlet, each individual outlet, their velocity distribution is uniform. Okay, which means that okay, if you look in the inlet, okay, the velocity along this y, if we assume this x and this is y, okay, the velocity on this y-axis is constant. And if you're looking like looking at this exit, okay, and if we also knowing that the velocity is also constant, across this cross-sectional, outlet, okay, area. So in that cases, okay, you can rewrite this equation just into this sigma form. So this sigma form means that you try to add in all this, scalar product between the velocity vector and the area vector, and add it to calculate this scalar product for all the inlet and the outlet exit, parts, and you add them together, it will be 0. Okay, and you need to be a little bit careful about this this v dot dA here, okay, because that since both of this v is a vector and the dA is a vector, and at the inlet, okay, so for example, if you have a pipe flow, okay, let's assume that we have this pipe flow at the inlet, so your dA, okay, this dA is a vector, so your area direction will be the normal direction of your this area, right? So usually this is your area vector direction, and if it is inflow, is inlet, your flow direction is usually going to right. Okay, so which means that at this inlet location, usually, okay, when you're using a dot v, do this scalar product, and if because that the velocity direction and area direction usually their angle between them usually will be larger than 90 degree. Okay, in this case this is 180 degree. So that which means that when you do this scalar product, you usually at the inlet you get a negative value. And if you're looking at the outlet, okay, so this will be the direction of your surface area, and this will be your velocity vector. So when you do this inner product between these two vector, and because that you can from here you can see that the angle between these two vector usually will be a value smaller than 90 degree, and in this case it is 0 degree. Okay, so when you do this inner product, this v dot a, you usually get a positive value. So which means that these things you do this summation. Okay, as we are seeing that if you're using this correlation here, you try to summation this vector, this inner product between these two vectors for all the inlet poles and outlet poles. For the inlet poles, this will usually give you a negative value, and for outlet poles will usually give you a positive value, and you add them together, you will get 0. So this is a mass conservation for this. If if under this rho constant and control volume constant, and also for this special cases that if you have uniform velocity at each inlet and outlet, so you can even convert from this one to this one. Okay, so be careful about when you do this inner scalar product. Okay, dot product between the two vectors, you need to consider that there angle, okay, between these two vectors. Okay, remember that if you have two vector, right? If you have this inner product, it will give you what? Right? It will give you that the magnitude of this A vector times this magnitude of this B vector, and times cosine alpha. Alpha is the angle between the two vectors, right? So this is this inner product means. This is one case here, and based on this, okay, since we have this v dot dA equal to 0, okay, we would like to introduce another concept that we usually use in the fluid dynamics, is the so-called volume flow rate. Okay, and the volume flow rate is usually defined by the mass flow rate over the density. Okay, and in these cases, okay, so let's first denote that this volume flow rate as this v dot dA, right? We know that this is the velocity dot dA, this is area. Okay, so this velocity dot dA is area. So if we times the rho here before it, we will get the mass flow rate, right? So let's denote that this Q is the mass flow rate, and you're knowing that this the correlation between Q and mass flow rate, this M is mass, all right? Mass flow, okay, is this divided by rho, okay? And let's denote that this is the volume flow rate, and it's which v dot dA, okay? And then you can calculate the whole volume flow rate for the whole surface from each inlet and outlet, okay? From area, you can just do integration on this one. And so if you define the volume flow rate in this way, simply means that in this case, if your density is constant, okay, if you integrate on all the volume flow rate for each inlet and outlet, okay, you integrate them all together, add them all together, your total volume flow rate will become 0. Okay, and because that, as I told you, is you will have the similarity. If on the inlet the sign will become negative value, and at the outlet the sign for that Q will become positive value. Okay, so this is just some a concept that instead of the mass flow rate, we can define a volume flow rate. So you can using this Q here to replace this v dot dA term, v dot A term here. You introduce inside this incompressible fluid cases for the mass conservation. Okay, and so that is the first special case, okay, which can simplify your mass conservation equation. And the second case where you can simplify your mass equation is that let's assume that it's a steady state problem. Okay, so which means that that the transient term is going to be 0. And this is our equation, right? This is our equation we derived for the mass conservation for the control volume. So which means that if you assume steady state, so this term will go to 0, because this is partial t. This is the transient term. So the only thing left is on the right this term here. Okay. So by assume that steady state, okay, we can simplify our mass conservation in this way. Okay, simply means that you know, if you do the integration of all the mass flux, you know, across over the whole control surface, you get 0. Okay, and similar things like the previous case, that if you have the case that where your velocity is uniform at each inlet and exit, okay, so, and then you know, you do the summation, okay, to calculate this term for each inlet and outlet, okay, and you add them together, so the final result should be 0. Okay, so this is also another case, another special case that you can simplify your mass conservation equation. So comparing to these two, okay, you remember that for this one, if you want to use this one, you need to use two assumptions. The first one is rho is constant. The second one is this volume is constant. And so for the second one, if you want to use this equation, okay, and you know, the assumption we made is that it's steady state. Okay, and so this is two special cases for this conservation mass conservation equation. Do you guys have any questions so far? Anyone? How we derive this mass equation? And what's the meaning of each term? No? Okay. So if there is no question, we are going to, you know, go over several example problems so that we can practice this formula, right? So how we can apply this mass conservation equation to solve real fluid dynamics problem. Please read this problem first so that we'll go over it together. All right, so this problem is pretty straightforward, right? And so you have a pipe here, and this is a drawn pipe. You have one inlet, okay, two outlet. Inlet is at 1, another two outlet at 2 and 3, location 2 and 3. And also you have small leak at this position 4. Okay, so you can consider that this is actually is 1 inlet and 4, sorry, 1 inlet and 3 outlet problem. 1 is inlet and 2, 3, 4 is outlet. Okay, and to do this problem, we need to define the control volume, right? So let's just define the control volume using this blue dashed line here. Okay, let's assume this is the control volume. And after we define this control volume, we simply need to apply this mass conservation law, okay, into this control volume. And since that for this pipe flow, right, we can assume that the velocity at this inlet, at this outlet, and this outlet, and also the whole here, let's assume that, you know, their velocity distribution, you know, is uniform. Okay, so we can just using this equation. Okay, and also this is a steady state problem, right? And also that we consider it's a constant density. Okay, so that we can just simply using this equation here. Okay, let's make sure. Yeah, we assume it's steady state flow, and also constant rho. Okay, so this will be our conservation equation, and just using this one, we can calculate all the result. For the inlet, we know the area here, this A1, and also we know the velocity, so we know the V1 and times A1 at the inlet, okay? And also for the this axis 3, we also know this A3 area, and also we know the V3. For this small hole 4 here, we know the mass flow rate directly. Okay, we know what this V dot A result will be, because this is the mass flow rate directly. And the question is that for this location at 2, right? This exit here, we know the area, but we do not know the velocity. The question is that ask us to calculate the velocity. So we just need to calculate each term, right? So basically, you're using that correlation we have here. This sigma, this v vector dot area I vector equal to 0. You simply get this v1 dot a1. This is that vector product, okay, between the velocity and the area at this inlet position, and this is the same product as the two, outlet position. And this Q4 is the mass flow rate is leaking as a small hole, okay. And so let's take a look at each term. So first, let's take a look at the inlet part, okay. And so V1 times A1. So if you're looking at this inlet location here, and as we know in that this A1 is the surface area, right? The location is A1 is this cross-sectional area of this inlet part, and the direction is always toward the outside, okay. So which means that at this inlet location it will toward to this direction, and the velocity, in the other word, because it's an inlet flow, so it's going to this direction. Now you can see that the area, vector and this velocity vector, they are opposite direction to each other. So in this way, when you do this dot product, you simply get this minus V1 times A1. Okay, so this is for this inlet location at 1. So we get this result here. This simply will be equal to minus V1 times A1. And for this the second term here, so this is the exit part at this exit location, okay, at the part 2. And in this cases, you can see that, okay, the area direction, right, is always surface the normal direction, but is towards to the outside, so it will go into this direction. And also because flow is flowing out, is also going down. So both the area and velocity, they are the same direction. Okay, so in these cases, when you do the inner product, you do the dot product between them, you get positive value, right? You got V2 times A2. Okay, and V3 dot A3 similarly, okay, although we do not know V3 yet, right? Because this V3 is the velocity we want to get as this part 3, we do not know it yet, and A3 we know it, okay. Similarly to this part 2, because this V3 is also an outlet part. So when you do the inner product, you will get a positive value from the V3 and A3, okay. And the last one, this part 4, that's small hole, okay. So for this small hole, we know the mass flow rate is 0.1 meter cubic meter per second, okay. And so this is volume flow rate at that location. And this is so because that part 4 is also considered as what I say, as an outlet and an exit part, right? Because the fluid is flowing out. So we can know that for this Q4, their value should be a positive value, right? So in these cases, we can simply substitute that 0.1 cubic meter per second for this Q4, okay? And you just substitute everything into here, right? V1 we already, so we got this final equation, and V1 we know it, A1 we know it, V2 we know it, A2 we know it, A3 we know it, we do not know V3, and Q4 is at 0.1. So you substitute everything, you can quickly calculate what this, okay, I think that we know the V3, A3, but we do not know V2, sorry, I make a mistake here. And then you can simply calculate what the unknown V2 will be from this equation. You just substitute all those power size and the velocity and into it, and also it's 0.1 here. You will get that for V2 value will be minus 4.5 meter per second. Okay, and so you get this negative sign here, right? what does the meaning of this negative sign? This negative sign simply means that, originally when we calculate this V2, right, we assume that this is the positive direction, right? Because that we're thinking that it's an outlet flow. But the result is showing us that because this is negative value, actually, because this becomes a negative value, actually the flow should be going up comparing to what we draw here, because this is the assumed direction. We assume that in this case it will be positive value. But the result give us a negative value. It's simply showing that at this location, actually it's not really a outlet for the flow. It's actually another inlet for the flow. Okay, it's because that the flow leaking from this port 4 and the flow going out from this port 3 is already larger than this inflow at the location 1. So you need some supplemental flow to going to inside from this port 2. Okay, so this port 2 will become an inlet in this case if you got the negative value. Okay, so this is a simple example, okay, to show you that how to use this mass conservation law, okay, in this fluid dynamics problem, so that you can quickly calculate the velocity, for this for flow inside the pipes, okay, by applying this mass conservation. So, any question regarding to this problem? No question? Okay. And this is the second example problem. Please read it first. Okay, so for this one, actually, this is the flow you see on the picture. Okay, this is a viscous flow. Okay, which means that the viscosity of the you need to be is considered, and that is why that this problem is called the flow over a flat plate. Okay, basically we will revisit this problem when we're talking about the viscous flow later on in the future chapters. So when you have flow over this flat plate, and because that the flow has the viscosity, okay, so there will be a friction between the flow and this solid surface. Okay, and at the location of the wall here, because we assume those non-slip boundary conditions, so the velocity of the flow will become 0. Okay, and then at the region very far away from the wall, okay, the flow velocity you will just be equal to your free stream velocity. Okay, that means that it will be form, okay, a very small region. This thickness of this region will be very small, and this region is very close to the wall, so that inside this region you will have a velocity gradient. This u direction velocity gradient, and this inside this region, okay, the velocity will quickly changing from 0 to the free stream velocity. And this small region, okay, where you have this gradient, the velocity gradient, and we are calling this region the boundary layer. Okay, and inside this boundary layer, right, for this problem, right, it give you that what this velocity distribution will be for this u as a function of this y. Okay, it give you this will be your u distribution, and this big U is the free stream U. Okay, and will be equal to 2 times this y over delta minus y over delta squared. Delta is the distance, okay, between this black line to this wall surface. Okay, so delta is also a function x. Okay, delta is a function x. This is some distance between here. Okay, out between here, and so from this equation you can see that if you make this y equal to delta, okay, if you make this y equal to delta, you will get u over u just equal to 1. Okay, which means that we assume that as the surface of this boundary layer, at this dashed line, the velocity will just become to the free stream velocity. Okay, so for this problem, the question we are asking that if we have this location, okay, at this location here, let's assume that we know this boundary layer thickness of delta is 5 millimeter. So this length is 5 millimeter. Okay, and if we draw a control volume in this rectangular defined by this A, B, C, D. Okay, and what we will see that in this control volume, and we will see that the flow will flow into this control volume through this A and AB, this AB surface, right? Because this is inlet. So the flow will flow into this control volume from this side AB, and also that we know that flow will also flowing out from this control volume on this edge CD, right? Because this is where the outlet will be for this control volume. But we also have some part of flow, okay, will flowing out from this upper edge BC. Why? Because that because that we know that inside this boundary layer, right? Because the velocity will be smaller than this big U, right? And so which means that you push this your flow up, okay, a little bit, so that there will be some additional flow will leaving on this boundary B and C. Okay, and so the question here is that what this mass flow rate will be, through this boundary surface B and BC. Okay, and so the solution for this problem is straightforward. We just need to apply the mass conservation law for this boundary, for this control volume. Okay, so basically what that mass conservation law will telling us? It's telling us that okay, if you add this inlet, okay, mass flow from this inlet, mass flow from these two outlet, using that correlation we had before, okay, using this correlation here, because it's steady state, this is going to 0. So if you do this correlation, rho times V times dA, and if you assume rho equal to constant, okay, so let's just assume that we can using this same correlation here, okay, we will get the result, and you cannot using this equation, okay, because this equation, this sigma equation form, which means you assume uniform velocity distribution on the inlet and outlet. You cannot using that one. Why? Because that we know that at this inlet the velocity is uniform distribution, but at this outlet the velocity distribution is not uniform. We follow this distribution here, and also on this side, okay, we do also their velocity is not a uniform one. Okay, so that you cannot using that sigma form for the mass conservation. You have to using the integration form. Okay, and so let's quickly do this one. Okay, this is the governing equation we are going to use, and let's assume it's incompressible flow steady state. So that's why its transient term is gone. And also, if we assume the incompressible flow, which means that this rho is constant, so this rho can also gone. Okay, and so what's the result we get? So we just need to calculate this integration between V and this dA on all these three surfaces, right? And it will be difficult to calculate it on this surface, but we do not need to do that because this question is asking us that what is the mass flow rate across this one. Okay, so which means that since altogether this one plus this one and plus this one, the mass flow rate from here inlet will be plus this mass flow rate outlet here plus mass flow rate outlet here is 0. Then if we want to get the mass flow rate here, we only need to know the mass flow rate from here and here, because that is all these three summation is 0. We know these two, we know the last one. Okay, so this is the last one is what we want to search. So we do not need to do the integration on this surface. We only need to do this integration on this surface and this surface. We can do that. Okay, so this is the equation we can have. Okay, if you do this on all the, if you do this mass conservation equation integration on all the control surfaces, basically you need to integrate on this all of these 4 surfaces, right? From the AB, BC, CD, and AD. And because AD is solid wall, so there is no mass flow no flow can flow in through this surface. So this is automatically become 0. Okay, and this one, the second term, this BC is what we want to get, because this will give you the mass flow rate through this BC, right? So we basically, which means that this term can be equal to 0 minus these two terms. Okay, 0 minus the mass flow rate from this surface AB, and minus this mass flow rate from this surface CD here. Okay, so we just need to calculate each of these two terms. The first one is easy to calculate it. Why? Because that the velocity distribution is uniform. So we know that the velocity is in this direction and area is in the inverse direction. So when you have this V dot A, basically you get the minus U dot times this A, okay? Or if you do this surface integration. And for the second one, and you have that velocity distribution as a function of Y, right? You have this velocity distribution as a function of Y. And also that we know that the direction of the velocity is on the right. So this this area normal is also going to right. So when you do the do the scalar product, so you just you get a positive value, and you just use the magnitude of the velocity times the magnitude area, and then you do integration from this y value from 0 to eta to delta. Okay, this is delta is given as 5 millimeter, right? So we can get these two terms. Okay, so for the first one, this term here, this is the left one from this AB surface. Okay, because the velocity is inverse, so it will be just you get a negative sign here when you do this scalar product. Times rho times this u. This is actually this u because it's a uniform distribution, right? So this u will be just become to this big U here, and you do the A here area. And we know that on this perpendicular direction, this plate width is small w. Okay, so the area on this surface is just w times this length, vertical length, which is delta. Okay, so basically this w times this delta will give the area. So your final result will be just minus rho times u and times the w delta. Okay, so you get this first term. Okay, the mass flow rate across this AB surface. Okay, and now you want to calculate the second term, which is the mass flow rate across this CD surface, right? You also do the integration, okay, rho u over dA, okay, because they are both the area and velocity is in the same direction. So you do this dot product, you get just the positive value, okay. So you get rho u actually cosine 0, okay, cosine alpha is 0, right? Rho u dot dA, and dA is the area of this surface, right, which will be W. So this plate width on the perpendicular direction of this screen, and times this y, right? W times dy, and this y you need to integrate it from the 0 to the delta. Okay, you need to integrate this y from 0 to the delta, and you substitute this u velocity, small u velocity, with this distribution you have here. Okay, you substitute it inside for it. You get this equation here. Okay, this integral, okay, both this rho w big U delta is constant, okay. You can just integrate this integral on this y directly from 0 to delta, and you will get this final result. Okay, after you calculate the mass flow rate on this surface AB and surface CD, and based on the correlation we have here, if you want to calculate the mass flow rate through this surface BC, it's just equal to negative this value minus negative value, because that from this is derived from this whole mass conservation. And you substitute these two integration result into that equation, you can quickly get what the mass flow rate from the upper surface there. Okay, what the BC value will be. It will give you a positive value because that we knowing that actually that the mass flow will basically from that surface is will going to flowing out from the control surface, this control volume. Okay, so this is another example problem, like how you can using this mass conservation, okay, for control volume. And any question here? No question? Okay. And for this example problem, we have an additional example problem, and I will leave this to your future recitation to go over it, okay? And if you're interested, you can also try to read it yourself. Okay, so we're talking about this mass conservation, right? And the next basic law we want to talking about is the conservation of the momentum, or in another word, it's Newton's second law. Okay, and this is the equation we introduced in the last lecture, right? So what is the Newton's second law in a closed system will be? F is this F is basically the resultant force for all the forces you apply to this system. Okay, this force can including both the surface force and the body force here. And at the right hand side, okay, this P is a linear momentum, and P is defined as m times v, right? The P basically is mv, okay. And this is called linear momentum. So it's telling us that this Newton's second law is telling us that for this system, the rate of the change of your linear momentum will be just equal to your resultant force. And also direction of this momentum and this direction of this force should be the same. Okay, and so this is how we calculate the linear momentum on a system. Okay, because the definition is m times or times v, right? So you can integration. If you want to calculate the whole linear momentum over a system, you just integration on this v over this dm, elementary differential mass, and you can assume that this dm equal to rho times dv, the volume. Okay, so you can write this form. All right, and now recall this differential correlation we just derived in the last class, right? This correlation we have here, this one here. No, not this one. Sorry, this one here. Okay, this is the correlation that differential between that differential in a system and the differential of the conservative quantity in a control volume. Okay, now let's this n equal to p, and make this eta equal to the v. Both p and v is a vector. Okay. So let's make n equal to this p linear momentum, and let's make eta as a velocity vector. So using that correlation, that derivative correlation between the derivative in the system and derivative in the control volume, okay, we can quickly get this one. Okay, we just replace p to that n and this velocity vector to that eta. Okay, so we get this correlation here. Okay, and so you can simply substitute this one here, the right hand side, into this equation here, right? Into this equation, into this one, because we know that this is equal to this one. Right? Just substitute this one into here, so we can immediately get what this Newton's second law will be in a control volume. All right, and also we want to consider the force, right? The force, okay. You may asking that the force in this equation is the force acting on the system. Okay, and if we want to change it to a control volume formula, we may also need to change this force from the system to the force or acting on the control volume, right? And they are the same thing, okay? For the force, actually the force working on the system and the force on the control volume, they are the same thing. Why? Because that when we remember that how we derive this derivative formula, we derive this derivative formula is based on the sketch we made earlier in the last class. We're using this sketch here, right? We're using this sketch here, okay? And then we make the limit make this delta t go to 0. We obtain that correlation between this derivative in the system and derivative in the control volume, right? And when the delta t going to 0, you will basically will go back to this initial state. And in the initial state, you can see that this system and this control volume, actually they are identical, right? When this delta t go to 0. So which means that the force working on the at this location, at this specific time, if this delta t go to limit to the 0, your force working on the system will be just equal to the force working on the control volume. All right. So it doesn't matter that you consider which kind of force it is, okay? You can just directly thinking that this force, okay, it's also, this force working on the system will just equal to the force on the control volume in this specific time t, okay? And so in this cases, okay, so this will be our final result. And remember that your force can write in the both two surface force and the body force, and it just will be equal to this term here. Okay, you will also the right hand side will also include in two terms. Okay, and so this equation here is just Newton's second law in a control volume for the fluids. Okay, and remember that we're also saying that Newton's second law also can be calling the conservation of the linear momentum, right? So in other words, you can also think that this is the conservation of the linear momentum, okay, under this control volume. So let's take a look at each term, right? We also want to get the physical meaning of each one. And before that, okay, we can also consider a special case. If we have units, uniform velocity, okay, flow at each inlet and outlet parts, you can write this integration on the surface flux. So this is a surface flux for the momentum flux, surface momentum flux, okay? Because that you have additional velocity. Before, in the mass conservation, right, you only have rho v, but now you have additional v. So this gives you the momentum flux, okay? And you can write this momentum flux in this condition using this sigma form rather than using integration if you have this assumption here, uniform flow at all the inlet and outlet. All right, and if you want to take a look at what the physical meaning of this equation here, okay, the left hand side is the force, right? So it does the force acting on the control volume, and on the right hand side, these two terms. What's the first term you did? The first term is that this is ddt, right? This v times rho over the whole volume. The rho, if you integrate on this rho over the whole volume, okay, this will give you the mass of the whole volume and times this v. Okay, so basically this is give you the whole momentum. This integration here will give you the whole flow momentum, linear momentum, okay, that p inside this control volume. So this, you add the ddt to it. So this will give you the change of the linear momentum within this control volume. Okay, and what this term will be similar to what that mass flux term, right? So remember that if you do not have this v, okay, you only have rho v times dot dA. That will give you this one, right? Remember this one? So this is the will be the, so now you add the v, this will become the momentum flux. So similar to that of mass flux, okay? This one will be the net rate of your momentum flux flowing out, okay? Because that there is no negative sign here, okay? This is the whole mass flow rate, momentum flux flowing out from your control, from your control volume through the control surface. Okay, so this will be the physical meaning. Okay, so the overall force will give, so we know that from the Newton's second law, right? The force will give you the change of the linear momentum, and in the control volume, okay, this form will change this linear momentum in two ways. One way is that the change the linear momentum with this control volume flow inside this control volume itself. Another one is that will also that making that equal, making the, you also need to consider the contribution that the change of this linear momentum due to the this momentum flowing out from this control volume. Okay, so this is the meaning of this momentum equation, okay, inside this control volume. And another thing you need to be careful is that so this is the equation for the vectors, okay? The force is a vector, okay? It has both magnitude and direction. And this term here, okay, you do an integration of this vector, so the result will be vector here. Okay, so this term will also give you a vector. And for this term, this v dot dA, right? So this is scalar product. So this product will give you a scalar, but this scalar will need to times another vector v here. So this one will also result in a vector. So this is your vector equation. And when you have the vector form of the equation, we usually, the convenient way we do is that we try to write their component for each vector, okay? So for example, if we define our coordinate system in a 3D rectangular coordinates, okay? If we define x, y, z direction, so we can write this vector equation into 3 component equation. We can write this on the x direction what the momentum equation will be. Okay, so in that case, this f will become fx, and this v will become u, and this v will become u here. Okay, and we can also write what the component of this vector equation in the y direction. In that case, we write this f as fy. We write this v as v. Okay, small v. And similarly, you can write the z component. F become fz, and this v becomes small w. Okay, and so on. So which means that if we have these 3D rectangular components, that vector form equation is equivalent to this 3 scalar form of the equation. Okay, which means that this Newton's second law we can write in this 3D rectangular form in these 3 equations for the 3 components on the x, y, z direction. Okay, so this is the force, fx is the force on the x direction, and this is small u is the velocity on the x direction. Okay, and this v dot a, which is still with the vector form. Why? Because this one will give you the product, give you the scalar. Okay, will give you back a scalar. So you cannot just replace this v as smaller u. No, because this value is is a scalar. You cannot decompose this term. Okay, you cannot decompose the scalar into 3 direction. No. So for this one, you still keep this vector dot product form. Okay, and similarly for the y direction and the z direction. Okay, and so we can also simplify this surface integration similar to the previous one if you have uniform flow at the inlet and outlet. Okay, so then you can simplify this surface integration here into this sigma form. Okay, so that you basically this sigma form means that you do the summation for all the inlet and outlet. Okay, so this is the momentum equation inside of a control volume. All right, and some special case. Okay, special case is that in the fluid dynamics, right? In many cases, when we are going to study it, the only body force we are going to use will be the weight, it will be the gravity. Okay, so that in most cases, okay, your body force can be given by that you do the integration on the whole control volume, and you do this rho is density times this g is the gravity constant, acceleration constant, and times this volume. Okay, and this will give you the whole weight, the weight of all the fluids inside this control volume. Okay, and which will be the mass flow. Okay, mass of the flow, the whole mass of this fluid inside the control volume times this g constant. Okay, and if we define this x, y, z so that this g is in the negative y direction. Okay, in that case, this body force, which means that if you write in this component form, this body force is only showing here, and you won't have the body force on the x and z direction. This two will be 0. All right, and similarly, okay, for the surface force, when we do the fluid dynamics, in a lot of cases we only consider surface force from the pressure. Okay, if we only consider surface force due to pressure, you can write the surface force basically by integration of the surface area. The surface area over the pressure times this area. Okay, and we have this negative sign here. Why? Because that we know that the pressure is what? Is a tensor, right? Sorry, not tensor. The pressure is a is the stress, right? And stress is the force over the area. So usually when we're talking about the stress in the last chapter, right, we define the direction of the stress. So what is the normal direction of the stress for the pressure? For the pressure, even P is larger than 0, it always means that your pressure is try to compress the fluid, right? So this is the direction that this P is larger than 0. Okay. On the left hand side is try to compress the fluid. On the right hand side is try to compress the fluid. On the on the bottom is going up. On the top is going down. So which means that this pressure, if you make it positive direction, if this pressure is larger than 0, okay, this positive pressure direction is always inverse your area normal direction, right? So this, if you do the area normal direction on this side, it will going to left. Area normal direction going to this side, you're going to right. So your area normal direction is always your pressure direction is the positive pressure direction. It will always be inverse of your normal direction. So when you do that, when you do this converted from this pressure to the surface force, right? If you want this surface force to be a larger positive value, you have to add a negative sign. So this negative sign is just try to guarantee that if we give this pressure scalar quantity, okay, we do not have a vector here, okay, for the pressure. So if we give this a positive pressure quantity here, and we can make sure that okay, we know that where this pressure force direction will be, because the pressure force direction will always inverse of your normal direction of your area, okay, because the pressure force is always inverse of normal direction. Okay, so the surface force due to the pressure is always the inverse of a normal area direction. So that's why we has this negative sign. Okay, so now you can see that okay, so this body force is also in this integration on volume, and surface force is the integration on the surface area. So you can also substitute these two terms back to the equations that this component equation that you have, or you can also back to this integration vector form of your component, this momentum conservation equation. Okay, so this is something we need to consider. Any question about this? About this, momentum equation, which is the Newton's second law equation for this control volume?
Professor?
Yes.
With the equation for the conservation of mass, wouldn't it almost be like the momentum equation, except you're just multiplying by the velocity vector? Is that the only difference?
Not only, it's like you also have this force here, right? Because that for the mass flow is equal to 0. Right?
Oh, okay.
Yeah,
so
for mass conservation of the mass, you have equal to 0, right?
Okay, so you're adding those two forces
equal to 0, and then for the momentum equation, not only you have the v here, you have another v here, you also have on this hand side you have the force. Okay, so you will see that this momentum equation and this mass equation, they look similar but just some special small difference there, right? It's because that the terms inside it have a similar physical meaning. Okay, that volume integration term is like the change of the things inside of the control volume, and that surface integration is the change due to that flow in flow out through the surface, right? That is what in the mass. And in the momentum, you also have these two terms. You have the change of the momentum inside this control volume, and also you have a surface integration. That is the change of the momentum due to this flow in and flow out, right? So that's why you see that they are close. But remember that for the momentum on this side, it's not equal to 0. You will have the force term. Okay.
Okay. Thank you, Professor.
No problem. Okay. And then the next task for us is that we are also going to try to practice this momentum conservation, right? Using some example problem to practice it. Okay. And remember that what the momentum equation it is Newton's second law, right? So if we apply the this momentum equation, to a fluid dynamics problem, it usually can give us what the force related things. Okay, the relationship between the force and the velocity, right? Previous example of problem, when we apply the mass conservation, what we use for that one? That one is usually give us correlation between the velocity and the area, because that we know that the velocity times area give us the velocity times surface, that cross-sectional area will give us the the mass, right? And this this volume flow, this momentum equation, when we apply it, it really give us that the force related regarding to that how the velocity is that the momentum is changing. So momentum is changing. It also means that velocity is changing, right? And another thing before I do that, another thing I want to mention to you is that these basic laws, right? Right now we introduce these two basic laws, right? The conservation of the mass, conservation of the momentum. They will working for the fluid dynamics at the same time. Okay, it not means that when I'm using the mass conservation, I do not so I cannot use the conservation of the momentum. No, okay, you can always apply both the mass conservation and this Newton's second law at the same time to a problem. Okay, and let's go over this example problem first. Okay, please read this problem description for it. And think about this, okay? So you'll see that the question is asking, this problem is asking that what the force will be. So which means that in this case, because it is asking the force, so we cannot just using the mass conservation to get the result. So we have to involve the momentum conservation. Okay. And for this problem, okay, so we have the flow, okay, flowing out from this nozzle, and this nozzle, we know that the velocity of the flow leaving out from this nozzle, and also we know that this nozzle area. Okay, so which means that we know that what's the how this flow, what the total momentum will going leaving out from this nozzle. Okay, and when this flow hitting this plate, right, and the flow direction will be changed. When the flow direction is being changed, which means that their linear momentum is also be changed, right? This because the P equal to mv, right? So this V on the originally is only on x direction, and after it hitting to this flat plate, it have to split. Part of the flow will going up, part of flow will going down, right? So this V is now changed from x direction to this y direction. Okay, and because we have this change of this momentum, so which means that we have to providing the force to make this change of the momentum become feasible, right? From Newton's second law. So which means that if you have a hand to hold this plate, okay, you have to have some force. This hand must be provided some force going left to hold on this plate to make sure that this can happen. Okay. And the problem for this question is asking that what is force is required from when you're holding this plate. Okay, and for this problem, if you're holding your hand holding this plate, you need both the force on the x direction and the y direction. On the x direction is used to to change this momentum direction. On the y direction, basically is the force try to hold to hold the weight of this plate. Okay, so the question is that what this force will be, and to do this, we definitely, of course, because this is related to the force, right? We need to using the conservation of the momentum, and we need to draw the control surface control volume. There are several ways to draw the control volume, and so this problem will discuss that we can define the control volume in the different ways. Okay, and both ways can give us the same result, but at the end you will see that one way will give you the result much easier. Mathematically you can get the result much easier. Okay, another way, although it gives you the same result, but the math involved will be more complicated. So this is the two ways you can define the control volume. The first way, this control volume in this blue dashed line, it will including both this fluid and also this plate itself, and it cut down at this hand here. Okay. The second way, we'll define this control volume. Okay, we will only include in the fluid. Okay, let's assume that this is dashed line here. Okay, and we're stopping this control volume will stop at this is the interface between the fluid and this plate here. Okay, and so we will going to using both control volume, okay, definition here to try to calculate the result. Okay, and the equation we are going to use is both the conservation of the momentum. So this is conservation momentum equation we had before, and also the conservation of the mass. Okay, so we are going to use both the conservation equation, conservation of the momentum, and conservation of the mass. And let's first look in the first control volume. With the first control volume, this CV1 we define here. Okay, and so in these cases, okay, and so let's consider that if we're using the control volume on the x direction, okay, because we are interested in on both x direction and y direction force, right? On the x direction force, we can write the x direction force. We can try to what I'm saying. This will be our control. This will be our momentum conservation equation, okay? And we make some assumption, try to make this equation simpler. First thing that we can assume steady state, so that the partial t term is gone. On the left-hand side, the term is gone. Previous equation, this is the ddt term is gone. So the only thing left is this surface integration. Okay, and so we only have this surface integration, and also that for these cases, okay, this at this inlet here, we can see that okay, the velocity is we assume the velocity is uniform distributed, and also at this outlet here and here, we can also assume that velocity is uniform distributed. So we can just simply using this sigma form here. Okay, so because this is the assumption we made, we assume that the uniform flow at both inlet and outlet. This inlet here, two outlet on the top and bottom here. We can use this sigma form. So your momentum conservation will just become to this one. Okay, and this sigma form, if we assume that this is x direction and this is y direction, so we can write two equations from this momentum conservation equation. One equation on the x direction and one equation on the y direction. Okay, on the x direction, we will involve the force, because this is the force equal to this one, right? You will need to involve the fx. On the y direction, you will involve fy. So let's take a look at the x direction first. Okay, so let's assume that you have this your hand, right? Let's assume that your hand will apply a force on the left direction, okay, at r of x. Okay, so you have this f of this is surface force, right? So let's assume that this Rx is the surface force provided by this hand, right? Because this hand is at this control surface interface, right? So, and for the body force on the x direction, we don't have any body force on the x direction, because that body force, the only body force for this problem, it will be the weight of the fluid. It's only on the y direction. So this body force on the x direction will become to 0. So the only thing left is this surface force on the x direction, which is given by this Rx. Okay, and if we assume Rx is going to left, so this will become negative Rx. Okay, because that we want this result force to go to right direction, to the positive x direction. And another question we will consider is that this this absolute pressure and gauge pressure, right? Because we want to thinking that the influence of this atmosphere pressure. Okay, so in this control volume, right? So we will have the one atmospheric pressure here, one atmospheric here, one atmospheric here. We have one atmospheric pressure on the all surface. So which means that if you're looking at this picture, so if you want to consider that the effect of the atmospheric pressure, on the left-hand side, you will have this atmospheric pressure. On the back of this plate, you will also have, on this side, you will also, so not back of the plate, on this side, you will also have the same this P of ATM. So they will cancel it out on this x direction. So we can just neglect the effect of this atmospheric pressure. Okay, and so that which means that the surface force due to atmospheric pressure is neglected. So the only thing left for this surface pressure is only this Rx here from the hand. Okay, and it will be equal to this this u is the x direction velocity and times this rho of this velocity vector dot this surface area vector A on each inlet and outlet. Okay, so let's take a look at this summation term here. Okay, and so let's take a look at this inlet, right? On inlet we have this velocity, this v velocity just going to right, right? And this area on this location area is going left. So this v dot A just give you negative v value times this area. This area is just this nozzle area, cross-sectional area of this nozzle, and the velocity v is just that velocity of the flow leaving the nozzle, right? So we can directly calculate this v dot A on this surface will be negative value v value times A, and also this u will also become that v value. Okay, so which means that in these cases, on this location 1, we will just equal to this minus v1 times a1 times rho. Okay, and I also times another u will be same velocity there. u1 will be v1 will be the same velocity at that location. Okay, so basically this will give you that our minus v squared rho a. Okay, and this v is this 50 meter per second is this nozzle velocity, and this area is this nozzle area. So we know this this v dot a, this summation at this location inlet. And what about the outlet? V dot a at the outlet, and at the outlet, okay, this v dot a is because area is going up and area going up, so v dot a is it will give you some positive value, but it doesn't matter, okay, because that this u, remember this u is the velocity at the x direction, and at the outlet here, all the velocity is in the y direction. So this u value at these two surfaces is 0. So no matter what value this is this vector product you get, so this when you times the u is always 0 because you don't have any x direction velocity at these two surfaces. So this term at these two surfaces will go to 0. So that means that the only term left, okay, when you do this summation is only that inlet flow inlet term. Okay, so by substitute this equation into here, and you can quickly get what this force, okay, this Rx you get, the force your hand need to provide on this x direction, you get it will be negative 0.25 kilonewton. You just substitute things there. Okay, this is the force you require to hold this plate on the x direction, so that makes this flow direction to change the momentum. And you get a negative value. Why? Because that the direction of this force has to go to the left, has to go to the inverse direction of the x. Because this is positive x direction, and this force has to go to left to hold on this plate, right? So that's why you get a negative value. Okay, so this is a result for if we're using this first method of the control volume. Oh, sorry. If we're using this first method of the control volume. And for the second type of control volume, we do not have time now, but I will continue this in the next class, okay, next Monday's class. And basically, the idea is that if we define the control volume is only on this fluids, you can also apply the same equation. But now, when you consider the force, okay, the force now will not be the hand force, this force, horizontal force from the hand. You need to consider the force from this reaction with this plate to this fluid, okay? And you can calculate that force. After calculating this force from the reaction force, and if you want to calculate the hand force, you also need to do another statics problem study from this plate, solid plate. You do your static analysis. You draw that free body diagram between the force of this plate, the reaction force, this hand force, then you can find the hand force. Okay, we'll continue that in the next class. And so I will finish it here. Okay, and so before I finish, we have attendance for to need to record for today's class. Okay, and go to your Blackboard. There are a quiz problem there. So answer that quiz problem. So that I can record your attendance. Do not forget it. You need to finish that quiz problem before 3 o'clock. Okay. Okay. Do you guys have any question? No. So if there is no question, I will just finish it here. All right. I'll see you guys next Monday. Okay. Have a good weekend, everyone.
Have a good weekend, Professor.
Thank you. You too.
Yeah. Bye.